way, I'm going to call upon one of our learners to open this session with a prayer. I will pick my namesake, Asimwe Daniel. Asimwe Daniel, can you pray for us?
Yes.
Yeah.
Oh Lord, Almighty Father, we thank you for the gift of life that you have given to us. We thank you for the gift of protection that you have awarded to us. Oh Lord, today we are going to start our lesson. Guide us so that whatever we learn, we get it into our brains and we get to understand it. I've prayed through Jesus Christ our Lord. Amen.
Oh, thank you so much, Daniel, for that wonderful prayer. Thank you. May God bless you. Now, we're going to start with the recap of what we started last time. Let me first share my screen with you. Let me share the screen with you. Hope you're able to see my screen. Hope you're able to see my screen. Can somebody tell me? Daniel, can you see my screen?
Yes, we are seeing it.
Good, thank you. So we are going to start. We're going to start right away with a recap of what we started last time. When we met, we started discussion on waves, where we said that wave is any disturbance that transfers energy from one point to the other point without the permanent displacement of the particles of the medium itself. We said waves can be categorized into two, and the first category was mechanical waves, and the other one was electromagnetic waves. By show of hands, who can define for us mechanical waves? Mechanical waves. Yes, I see an attractive name here, Bright. Akatondrana. How are you? Were you in that lesson? You are not in the lesson, it's okay. Who was there? Can you raise up your hand and you tell us mechanical waves? What we said was? Yes, Abigail. Rocky? Rocky, Abigail? Okay, Rocky, Abigail, can I talk? Let me hear from Rachel. Rachel?
Mechanical waves are waves produced by disturbance of the particle of the medium, and they require material medium for their transfer.
Very good. Very good. Actually, you have made it all. So we said mechanical waves, these are waves which are produced by the disturbance of the medium. Disturbance of the particle of the medium, and they also require material medium for their transfer. An example, like one only. An example? Who can raise the hand and tell us?
Please pardon.
Yes, Charity.
Water waves.
Very good. Hillman.
Sound waves.
Very good. Gloria.
Waves in streams.
Wonderful. Good. So those are the examples of mechanical waves. Let's talk about briefly electromagnetic waves. Who can define for us electromagnetic waves? Yes, bright. Electromagnetic waves. Electromagnetic waves, bright. Okay. Who can define for us electromagnetic waves? JB.
Yes, sir.
Yes, electromagnetic waves.
Electromagnetic waves. These are waves made up of electric and magnetic vibrations of high frequency.
And they do not require material medium.
Yeah.
Very good. An example?
Microwaves.
Very good, very good. Very good. Innocent, can you give us the second example of an electromagnetic waves? Innocent? Okay. Akimo, can you give us an example?
Radio waves.
Radio waves, very good, very good. Philomena, can you give us another example? Philomena? X-rays, very good, very good, very good. So others, we said ultraviolet and so forth. So we did not stop there. We also went ahead and we said there are wave can also be classified into wave motion. We said wave motion is just a form of means of transfer of energy, and wave motion is classified into two. We said there is what we call to be transverse and longitudinal, where you said that transverse waves are those waves in which the direction of vibration of the particles of the medium is perpendicular to the direction of the wave travel. And we gave an example. We said all electromagnetic waves are transverse. Then we talked about longitudinal waves, where we said longitudinal waves are the types of waves where the direction of vibration of the particle of the medium is along the direction of the wave travel. And a typical example which you gave was sound waves. So we looked at the differences. We looked at the differences between longitudinal waves and transverse waves, between mechanical waves and electromagnetic waves. Good. So we did not receive notes for the first lesson, and we didn't copy all of them down. When are you going to be teaching? Good. I sent the notes. The notes are already on our Google Classroom. At the end of this lesson, we shall show you how to use Google Classroom. That one is David. David, I sent the notes. Even I gave the assignment. Some of you have already done even the assignment. Session account, I don't know your name. Please write your name well. Repeat the definition of wave. Yeah, we said wave is any disturbance that transfers energy from one point to the other point without the permanent displacement of the medium itself. Let me hope I'm clear. The person who asked for the definition of wave, is that okay?
Yes.
Very good, very good. Please, in case of anything, don't hesitate, just ask questions. We shall answer it. We are here for you. Is that okay? Me, I like class which can ask questions. A class which can ask questions is the best class ever.
I beg your pardon on waves.
Definition of wave, we said a wave is any disturbance that transfers energy from one point to another point without permanent displacement of the medium itself. That is what we call to be wave. So today, for the newcomers, those who never attended the first lesson, my name is Teacher Daniel Alera. Okay? And this is Senior 3 Physics class. I'm a teacher for Edify Uganda, which is supported by ICC Teachers Association. Good. Today we're going to see something very interesting, that is terms in waves, terms which are used in waves, and also wave equation. To start with, let's see, we shall consider the two figures you see. We have two figures. There is this figure. There is this figure. And there is this figure. So we are going to define them from here before we move to the next slide. I will start with this P2. Do we all see the distance P2?
Yes.
P is here, and this is what? This is 2. Is that okay?
Yes.
How do we call the distance P to Q?
Pardon.
How do we call the distance P to Q? Somebody said wavelength. Let me see somebody else raise up their hand. Yes, Joyce.
The amplitude.
Very good, very good. Let me clap for you. Very good, very good. It is called the amplitude. Is that okay? Good. Who can define for us an amplitude as far as wave is concerned? What is amplitude? Amplitude? Yes, Esther? Esther?
Amplitude is the vertical displacement of a wave from its rest position.
Vertical displacement of a wave from its rest position. Thank you. Thank you so much. Good. Daniel?
Is the maximum.
Very good. I wanted that word maximum. Very good. That word maximum. Do we all hear that, class?
Yes.
You have to put the word maximum. So it's the maximum displacement of the wave particle from the resting position. Is that clear? If you don't want to call it rest position, you can say from equilibrium position or from zero position. Is that clear, everyone? Rema, you are telling us. I see Rema. Harriet is saying, good morning, sir. Could you please provide the Google Class link for Senior 3? Yes, we shall do that. Then Rema is saying amplitude is the maximum displacement of the particle from rest position. Very good, Rema. That is very correct. Okay. So that is our amplitude. Maximum displacement of the wave particle from resting position. Then we have this. Do you see this symbol? This one. This one is, we call it to be lambda. Hello, let's meet ourselves. Let's meet ourselves. Let's meet ourselves. So we are saying we all see this symbol, no so?
Yes.
Good. It is called lambda, which represents wavelength. So how do we define wavelength? Who can define for us wavelength, which is the next term? You can raise up your hand. Donald, wavelength?
Yeah.
Yes, Donald, wavelength. Okay, let me go to Kevin. Kevin. Kevin, you can define for us wavelength. Okay, let me go to Ampere.
Wavelength is the distance between two successive pressed chord tracks.
Very good. Distance between two successive press or trout is what we call to be wavelength. I guess there's somebody with another definition.
What happened?
Semakola. Semakola, can you define for us wavelength? Semakola? Can you define for us wavelength? Wavelength is the distance between two successive particles. That is from Ivan. Semakola, can you define for us? This is the distance occupied by one complete circle. That is the, who is that? Mugisha Ivan.
Wavelength is that this.
Distance. Okay, we can't hear. So we are saying Jovia has written here. This is the distance occupied by one complete wave. Good, Jovia, that is correct. Good. Somebody saying Betty Berry is saying that teacher, we can't hear you. I don't know whether the problem is hers or mine.
I'm not hearing you.
You're not hearing me, Betty?
Those people should mute, then we shall hear.
But the rest can hear me, eh?
Yes, we can.
The distance between two particles. Who is Edward Tendo? Edward, are you there? Edward?
I'm there.
Please, I want to hear that definition. Speak it out, my brother.
This is the distance between two successive particles in a phase.
Very good. Actually, you have taken all the marks, my brother. Good. I like that definition. So, other members, we shall say wavelength is the distance between two successive particles which are in phase. I'm going to explain what phase is ahead. Good. Let's see some of those terms used. We've seen amplitude. Amplitude is the maximum displacement of the wave particle from the equilibrium position. This equilibrium position, we also said it can be called rest position. This rest position can as well be said as zero position. So the maximum displacement of the particle from the equilibrium position is what we call to be amplitude. Then wavelength. Wavelength, we have already said, it is the distance between two consecutive. If you don't want to use the word consecutive, you can use the word successive particles, which are in phase. It is exactly what our brother has just given us. Now, we are going to talk about, Donald is saying wavelength is the distance between two particles which are in phase. Very good, Donald. Ruth? Yes?
What is a phase?
Yes, it's what we're going to see now. Particles are said to be in phase. Do you see that?
Yes.
Particles are said to be in phase if they are in the same point, in the same path, at the same time, and moving with the same, in the same direction. You may not understand that very well. Let me draw something here. Do you see what I'm doing here? You've seen that circle, no, sir?
Yes.
Good. If I divide into 4 quadrants, I hope you have studied trigonometry in senior 2, senior 3. This is 0 degree, no, sir? Isn't this a 0 degree?
Yes.
This is 90, no, sir?
Yeah.
Then here we have 180. Is that okay?
Yes.
Yes.
Then here we have 200 and what?
70.
70.
Yeah.
Then lastly here we have what?
300
and what?
360.
60. Good. Now let me call this point to be point A. This point to be point B. This point to be point C. This point to be point D. And this point to be point E. The one that corresponds to 360, we are calling it to be E. Is that okay?
Yeah.
Now, when you look at a particle which is at point A, okay?
Yes.
And a particle which is at point B, do you see that?
Yes.
These two particles are not at the same point. Have you realized that?
Yeah, we are seeing.
Yes.
So we say that they are not in phase. They are not in phase. Why? They are not at the same point. Okay?
Yes.
But when you see the particle at point A, okay?
Yes.
And particle at point E, are they not at the same point?
They are.
But do they have the same angle?
No.
No. They are at the same point. They don't have the same angle, but they are the same point. And so we say the particle at A and the particle at E are in what?
Phase.
Are in phase. Let's get what a phase is now.
I beg your pardon, sir.
So we are saying when you consider a particle at A and a particle at E, okay? They are at the same point and different angles. Is that okay?
Yes.
So, particle A and particle E are said to be in phase. You see that? I want to refer you back to the diagram. Okay. Are you seeing? Please mute yourself. Mom, mute yourself. So we see this particle is at O. So this is 0 degrees now.
Teacher?
Yes.
Excuse me.
Yes.
Is it okay if I mute all of them, then the one who raise up the hand, you ask them to unmute?
It's okay, but now we have to alert them to be sending their questions maybe to chat.
No, what I mean, like if a learner raise up the hand, you are the one to tap on that learner, you ask to unmute. Because the noise is too much.
Okay.
Yes, I've done that. For example, you can tap on Joyce and ask her or him to unmute.
Okay. So I see some hands up here. Yes, Angela? Angela? You can unmute yourself.
You have to tap on Angela if you have chosen Angela.
Yes, I've tapped on her. Yes, Angela, do you have a question?
No, you've answered it.
Okay, please. Fine, thank you. So, we are saying, when you look at point O is at 0 degrees, point B, this is 180 degrees. Because it's a half a circle. Then this is another half a circle, so it makes this one to be 360 degrees. If you remember, we said a particle at 0 degrees and a particle at 360 degrees are at the same point, and so they are said to be in phase. So that makes the distance from point O to point B to be the wavelength lambda. Let me hope it's clear with everyone. Good. I see Bette with the hands up. Bette, can you unmute yourself and you tell me? Bette? Okay. Donald, is there any problem?
Yes, sir. May you please
Yes,
pardon?
please go on.
May you pardon what you have said about the lambda? About the I didn't understand around here, around the diagram.
This diagram, this one, okay?
Yes, about the diagram that's here.
Yeah, we said the distance. We said if a particle is at 0 degrees, if a particle is at 0 and another particle is at 360 degrees, okay? Yeah. From the previous diagram, we said these two particles, we saw that these two particles are at the same at the same point, and so they're said to be in what? They're said to be in phase. Is that okay?
Yes.
And we see the distance between any particles which are in phase is called to be lambda, is the wavelength. Is that okay? So when I bring you back to this diagram, you see that the particle at O is at 0 degrees. Then the particle at A is at 180. The particle at B is at 360 degrees. Is that okay? And so, 0 and 360 degrees, they are in what? They are in phase. So if they are in phase, the distance between those two particles is what we call to be the wavelength lambda. Is that fine?
Yes.
Very good. Let me move to the next thing. So the same two particles are said to be in phase if they are at the same point in their path and they are traveling in the same direction. Another definition of wavelength is the distance covered in a complete circle of a wave. So if a wave performs one complete cycle, then that distance is what we call to be the wavelength. Is what we call to be the wavelength. Good. I see some hands up. Emmanuel? Emmanuel, do you have anything to say? Emmanuel? Okay. Akimo, do you have anything to say?
Yes, teacher. Teacher, pardon about the wavelength lambda. I'm not understood.
Yeah, we said lambda is the distance between two consecutive particles which are in what? Which are in phase, okay? two particles which are in phase, we say that if we have a wave traveling like this, this particle, okay, do you see here? Do you see here? And this particle are in phase. So these two particles are in phase. So the distance from here to here is called lambda, which is the wavelength. That is our wavelength. Yes, Rachel? Rachel?
Are we allowed to write and mute in the paper?
Are you allowed to?
Are we allowed to write lambda in the exams?
Yes, that symbol is known. But as long as you define it, you say, if lambda is the wavelength, then you move on with other steps. Is that okay?
Yes.
Good. Let's move on. So you're saying that it's also a distance covered in a complete cycle of a wave. And there's an NB here. The distance between two consecutive crests or troughs in a transverse wave is equivalent to wavelength. So when I am talking about distance between two consecutive crests, let me draw it here. If I have this as my wave, this one is a crest, this one is also a crest. So this distance is also called to be wavelength. But it's not the definition. This distance is also wavelength lambda. Distance between two consecutive crests or troughs is also called to be the wavelength lambda. Yes, JB? JB?
So I was asking whether I could define the wavelength as the distance covered by the wave profile in a periodic time.
Yes, that is also very good. When you bring now periodic time, that distance covered in one period is also the wavelength. Thank you so much, JB. That was good also. Good. Let's go to something else. And that is terms used still. Term number 4 is frequency. I guess you know frequency. Frequency is the number of complete cycles which are made in 1 second. Number of complete cycles made in 1 second is what we call to be frequency. And its SI unit is hertz. That is SI unit of frequency, it's hertz. So by definition, hertz is the frequency of a wave which makes one complete cycle in 1 second. So if a wave makes like one complete cycle in 1 second, that one is called to be hertz. Yes, Akimo? Yes, Akimo.
Can't you give us another alternative of frequency?
Okay, another alternative is the number of oscillations made per second. Is that okay? Number of complete oscillations made per second. Is that okay?
Yes.
Do you have another alternative also?
No.
Okay, so if a wave makes like 20 oscillations in 1 second, that means that its frequency is 20 hertz. Is that clear, everyone?
Yes.
Good. Yes, session account. I don't know your name. Please rename yourself. I see your hands up.
Olivia.
Olivia.
Yeah.
Yeah, Olivia, you have a question. Do you have a question?
Yes, I do.
Please go ahead.
Can you please
explain more about the difference between frequency and period.
Oh, the difference between frequency and period. But have you got the definition of frequency already?
Yes.
Good. Now, period is defined as the time taken for a wave to make only one oscillation. Okay?
Yeah.
The time taken for the wave to make only one oscillation. That is period. While frequency is the number of oscillations made in 1 second. Is that clear?
Yes.
Yeah, very good. I see Faith with the hand up. Faith? Yes, Faith. Okay, let me, Bright?
Yeah, I would like to give another definition for period.
Welcome, it's very welcome. Yes?
It's the time taken for a wave to travel one full wavelength.
Good, good, good. You guys are dangerous. You people are not easy. The time taken for a wave to travel a distance which is equivalent to one full wavelength. Remember, one full wavelength is a complete cycle. Is that okay?
Yes.
One full wavelength is a complete cycle. So the time taken to travel a complete cycle, the time taken to make one complete oscillation is the wavelength, which becomes now one complete oscillation, one complete cycle. That would be that. So hertz
Yes, Chair.
So that is that when it comes to hertz. Let's see something else, and that is NB. It is very important to note that one frequency equals to 1 over period. Okay? If I know the period, I can easily get the what? I can easily get the frequency. So to get the frequency, I divide 1 by the period. So you're saying period is 1 over frequency. That means that frequency is also 1 over period. Yes.
What is the difference between a frequency and period?
I've already said it. We said frequency is the number of complete oscillations made in 1 second, and period is the time taken for a wave to make one complete oscillations. Do you hear that?
Yes.
Good. Emma is saying that period is the time taken by the wave to perform one complete oscillation. Yes, Emma, you're very correct. Good. Let's move to something else. That is period. We have talked about period. We are saying period is the time taken for the wave to perform one complete oscillation or one cycle. It is measured in what? In seconds. And also, we said that frequency was 1 over period, so that means that period is also 1 over what? 1 over frequency. Is that okay, everyone?
Yes.
Is it fine?
Yeah.
Good, 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 good. I want you to see that NB which is in red. Do you see that NB which is in red?
Yes.
One period corresponds to a distance equal to the wavelength. One period corresponds to a distance equal to the wavelength. I see Daniel. Daniel, you have your hands up. Yes, Daniel? Daniel, unmute and talk.
Sir, is there any other word to mean oscillation?
Oscillations? Yeah, you can use the word. You can use the word cycle. Is it okay?
Yes.
Yeah. Okay. Up, Tracy, up. You can say something.
So can you put on the definition of hertz?
Hertz. Okay. We said hertz is a wave in which makes one oscillation in 1 second. Hertz is the frequency of the wave which makes one oscillation in 1 second. A frequency of a wave which makes one oscillation in 1 second. Is that okay?
Okay.
Good. Yes, Monica. Gift Monica. Yes, Gift Monica. If Monica, you can unmute and talk.
Is there any word we can use to mean correspond?
Hey, correspond. The word that we can use to correspond. Yeah, you can say equivalent. You can use equivalent. One period corresponds to the distance equal to one wavelength. It is equal to the distance equivalent, or you can say it's the time that is used to cover a distance of one wavelength. But the word corresponds is the only simplest term we can use. Good. Let's go to something else. Caleb is saying his network is killing him. Sorry for sure, Caleb. All will be fine. Let's move to something else, and that is terms used in wave steel. Cycle or an oscillation. Cycle or an oscillation is a to and fro, going forward and coming backward. When you go forward and you come back, we say one cycle. Go forward and come, say 2 cycles. Is that okay? So that is what we mean by cycle or an oscillation. An oscillation is to and fro movement. Is that okay?
Yes.
Very good. Then there's this next part, which is called wave front. Wave front, we are saying a wave front is a section through an advancing wave, or it's just a region in a wave where all particles are in what? Are in phase. We've already seen that all the particles are in phase if they are all at the same point, in the same, when they're traveling in the same direction. So there is a point always on the wave where all particles are always in what? Are always in phase. So that point where all the particles are in phase is called wave front. I always use water wave to demonstrate this. If you have water in the basin, then you drop a stone there, you will see something like this. No, so you will see something like that. You will see something like this. Is that true anyway?
Ripple tank.
Very good. You see something like you see a ripple tank. No, so? So here, this line, it is always a heap of water molecules. This one, you find that there is a heap of water molecules, and here there is a heap of water molecules. So that means that all water particles, all water molecules are concentrated here. They are at the same point, they are at the same point, they are at the same point. So these three regions, we give them a name, wave what? Wave front. So we will say a wave front is a region or is just a place where all particles are in what? Are in phase. Now, if I draw a straight line here, do you see that? If I draw a straight line here, which is perpendicular to the wave front, perpendicular to the wave front, perpendicular to the wave front. This line which is perpendicular to the wave front, it is called ray. A ray. So a ray is a line which is perpendicular to the wave front and it shows the direction of the wave. Then a wave front is a point or a region on an advancing wave where all the particles are in phase. Rema is telling us here, Rema is saying that wavefront is a line or a section taken through an advancing length where all the particles are in phase. Very good, Rema. Very, very good. Very, very good. We have Paul Bigo. Wavefront is any line or a section through an advancing wave in which all particles are exactly in phase. Good, Paul. Very good. Very, very good. Good. Okay. This is so great, so nice, so interesting. Let's see. This is the definition of a wavefront. A section through an advancing wave where all particles are in phase. Yes, Wilson? Wilson?
I wanted you to pardon me the explanation of wavefront.
Wavefront. I think, is it okay now?
Yeah.
Okay, please. Thank you. I see Monica, gift Monica.
Yes, sir.
Hello, I see your hands up.
Yeah, master. I'm my definition.
Yeah, you are submitting your definition.
Yeah, of wavefront.
Please go on, or I've already read it.
It is a surface or a through a wave joining particles that are in phase.
Very good. It's a surface or a point which are joining two points which are in what? Which are in phase. Very good. Good. So that's a wavefront. Then we have a ray. A ray is the line perpendicular to the wavefront and it shows the direction of the wave travel. Good. So those are briefly some of the terms used in waves. Now we are going to do one more thing before we see some others, and that is wave equation. So let's see wave equation, okay? Who can state for us wave equation? What does it state? Well, how does it state? Just state it for me. Who can state for us wave equation? Yes, Angela. Yes, Angela?
Velocity is equal to frequency lambda.
Very good. Oh God, oh God, oh God. God, I thank you for this class for sure. I've enjoyed this class. Good. Good, 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 good. Velocity equals to frequency over times lambda. Very good, very good. Teacher, how can we make it to Google Classroom? We shall take you through. That is Akim Bure from the chat. We shall take you through, don't worry. So we're going to start with wave equation. But before you derive wave equation, I want us to be careful here. I will give 3 statements before we start the derivation. The first statement is the definition of wavelength. We said wavelength is the distance between 2 consecutive particles which are in phase. Do we all hear that? Master my statement very well so that we don't suffer in deriving. Distance between 2 particles which are in phase. Please, that one is that. Or the distance covered by one complete cycle of a wave. Do you hear that or? That or is the most important one. The distance covered by one complete cycle, a complete cycle. That is one statement. Then the next statement is the definition of period. A period, we said that it's the time taken. It's the time taken for the wave to perform one complete oscillations. Yes, Ivan, do you have a question? Yes, Ivan? Okay, so we said there are three things. One, wavelength is the distance covered by one complete cycle. That is one. Then period is the time taken for the wave to make one complete cycle. The 2 statements are very interesting. Time taken for the wave to make one complete cycle. That is the period. What about one complete cycle? One complete cycle is equivalent to the wavelength. Do you hear that statement? Are we hearing that statement very well?
Yes.
One complete cycle is equal to the wavelength. And the time taken to make one complete cycle is the period. Do you hear that? So that means that if a wave makes one complete cycle, the time taken for the wave to make that one complete cycle is the period. But that one complete cycle is the wavelength. So that means that if the distance covered is wavelength, what will be the time taken?
Pardon.
If the distance covered.
The distance covered.
Pardon the question.
Yes, that's what I'm trying to repeat. If the distance covered, if the distance covered is the wavelength, what will be the time taken? Yes, Emmanuel.
The distance covered is the wavelength.
Yes, Emmanuel.
Time.
What will be the time taken? Yes, Emmanuel.
The distance covered
will be one out of the wavelength.
1 out of the wavelength. Good trial. But let me repeat my statement. Very good. Aha! Akimo, thank you so much. Akimo, I want you to Maggie. No, I will not read this one, but I want you people to speak it out. Akimo, unmute yourself. I've given you that permission. Akimo? Akimo, you speak your answer. Okay. Sharon says it's equal to the period. Very good. Persist says equals to the period. Very good. You're finished me now. So, if the covered is the wavelength, then it is clear from our definition that the time taken is the period. Is that okay, everyone?
Yes.
Yeah.
Good, good, good. Let's derive it then. So we are first defining what wavelength is. This is the equation which relates lambda, which is the wavelength, frequency f, and the velocity v of the what? Of the wave. Is that okay?
Yes.
Somebody has already told us that v equals to f what? F lambda, not so?
Yeah.
Yes.
Good. So let's start with the derivation. We start from the definition of velocity. Who can define for us velocity? I mean, the formula for getting velocity is in form of distance and time.
Speed equals to?
Yes?
Speed equals to distance over time.
Very good. Very good. Very good. You go to campus for sure, even though you're in senior 3. Yes. You just go to campus direct because you know most of the things already. Oh God. Thank you for giving me this class. Please, I don't want anybody to miss the next lesson. Is that okay?
Yes.
Yes, I want to be with you surely, for sure. So we start from the definition of velocity equals the distance divided by what? Divided by time. Is that okay?
84. Neighbor to Seko ku 95. Back on the door.
So if that is the case, then we say if a wave covers a distance equals to the wavelength, that's the statement I've been saying. If the wave covers a distance equals to the wavelength, then the time taken is supposed to be equal to the what? The time taken is expected to be equal to the period. So, don't know what we do. So, where there is distance in this formula, do you see the formula velocity equals to distance over time?
Yeah.
So where there is distance, we shall substitute wavelength lambda. Is that okay? So this one becomes lambda, then divided by the time is what? The time is period. Is that okay?
Yes.
Very good. Now, that means that our velocity equals to distance over time. Our velocity will be lambda over what? Over t. Is that okay?
Yes.
Yes.
But I want us to see that expression, the next expression. Do you see that expression?
Yes.
Lambda equals to 1 over t. Is it okay with everyone?
Yes.
Okay, good. Then what did we say is our 1 over t?
Frequency.
1 over t, we said it was frequency. So when we substitute it there, where there is 1 over t, we substitute f. Is that okay?
Yes.
So that means V equals to lambda what? Lambda F. Is that okay?
Yes.
Is it fine with everyone?
Yes.
Yes.
Good, thank you. Thank you so much. Is there anyone with any question? Angela? Akimu?
No question.
Or Paul? Paul, do you have anything you want to add on? Okay. What about Anthony Tugume? Anthony Tugume? Anthony Tugume? Okay. If there's no question, please allow me stop here for now. But in our next lesson, do you hear that?
Yes.
In our next lesson, we are going to start right away from the calculations. Is that okay?
Yeah.
Yeah, but this work, I'm going to post it on our Google Classroom.
So how can we access the Google Classroom?
Exactly. That's what we are going to discuss here briefly. We're going to discuss Google Classroom briefly, and then we see how you can join there. Can I call upon Mr. Bernard?
Thank you, Mr. Aria, for the wonderful session.
Thank you so much.
We are inviting all learners to attend the session that is starting at exactly midday. We are going to handle things to do with classrooms, the Google Classrooms, and the other platforms that we want them to learn. So please be there at 12 to attend the session. Is that okay? We shall handle it from start up to the end at 12, that 1 hour only. So attend from 12 to 1.
On this app?
We, if you check in the group, we have shared the link.
Okay.
Yes, we have shared the link for you to attend that session. And those who are not on the link, I mean who are not on the group, can I know them? You can raise up your hands and then we can share the what? We can share the link, the details. Those who are not on the chat, on the group chat, I've shared, pick the link there. Just write down the code. Write down the code and the password. If you want, you can also take the link, copy in the chat. Are we there?
Yes.
Copy in the chat. And for those who are not in the WhatsApp group, let me send you a link. Let me send you a link. Send you the link. I've also shared the link in the chat for the WhatsApp group.
Where is it, sir?
Hasn't arrived. Check.
Is there in the chat? Just go on the chat.
Then I've said for Google Classroom, let's be there at 12 to attend the entire session. Okay? Let's attend the entire session and learn how Google Classrooms are going to work, because we can't post work on WhatsApp. We have to put it in a central location where all of us will access at any time we join. So have a great day. See you in the meeting.
Sir, are we having an English lesson after lunch today?
Today, Friday, yes, we have a lesson at 2 p.m. English.
Thank you, sir.
Okay, see you.
Okay, thank you so much, Mr. Ben.